Imagine dropping a marble on a stretched sheet. The fabric bends and anything nearby rolls towards it. Now, replace that sheet with the very fabric of the universe, space-time. This is the essence of Einstein's general relativity. For centuries we believed gravity was just a force pulling objects together. But Einstein shattered that view. He showed that mass and energy warp space-time itself, bending the paths that objects and even light follow. In this video, we are going to explore the fascinating concept of space-time curvature and how Einstein's general relativity changed the way we understand gravity. My name is Shaunak and you are watching this video on my channel, Physics for Students. Welcome to this new lesson and understanding of space-time curvature and its connection with general relativity. Well, first we will look in what is a space-time curvature and how it actually shapes our understanding of general relativity. General relativity is the geometric theory of gravitation published by Albert Einstein and others in 1915, and it is the current description of gravitation in modern physics. General relativity generalizes special relativity and refines Newton's law of universal gravitation, providing a unified description of gravity as a geometric property of space-time or a four-dimensional manifold, and this leads to certain other cosmological frontiers to open, such as black hole, neutron stars, white dwarfs, and so on. The concept of straight lines, however, got generalized into what we now call as geodesics. Also, the basic essence is the same. It is the shortest possible path traveled between 2 points. Also, we see that time and space, which was treated as two different identities, were now treated as a space-time continuum. And we are going to explore that this shift from space-time to space-time continuum carries us a profound change in terms of our understanding. The entire area or the edifice of general relativity depends only on this one, which is called Einstein field equation, which are a collection of 16 minus 6, 10 partial non-linear differential equations, and most importantly tensors and the mathematics of tensor. Now, these led to various other areas of research like cosmology, black holes, gravitational time dilation, and gravitational waves. And these are not theories, but the current scope of research and telescopes have proved that these things exist. Now, overall, this is all in all what we call, in a glance, what is general relativity all about. Now, it actually started with the collaboration of Albert Einstein and his very old friend Marcel Grossmann. As you can see, this is Marcel Grossmann in the picture and this is Albert Einstein. Well, who are the rest? I leave up to you. If you know, you can put up the comment in the comment box. Now, the Einstein and Grossmann's 1913 paper, which is the English translation, says Outline of a General Theory of Relativity and a Theory of Gravitation. This is commonly referred to as the Entwurf paper, was a key step in the development of general relativity. Although it was an intermediate formulation and later revised, it introduced crucial ideas that shapes Einstein's final 1915 theory. Well, the Entwurf document actually were not complete. I mean to say they were not fully correct because they lacked what is called a covariant theory of gravity, but it is quite noteworthy that the 1913 Entwurf paper is an essential stepping stone to understand the current scope of general theory of relativity. However, in 1915, this was totally abandoned as Einstein found something new. And this was basically this paper, the original paper written in German. Translated to English, it is called Reports of the Royal Prussian Academy of Sciences, Einstein, the Field Equations of Gravitation, Berlin 1915. And this was published by the Royal Academy of Sciences in commission with George Reimer. Well, this paper particularly carries importance because this was where Einstein's field equations came in. Now, most importantly, using his new equation, Einstein very famously explained the perihelion shift of Mercury, which has baffled for physicists, and even Newton actually connected kind of a correction which was wrongly calculated by Newton, and it was actually 43 arc seconds per century, which was beyond the capacity of Newtonian mechanics to understand. It also led to very important phenomena which is called the gravitational time dilation or the bending of light. though it did not fully appear here in 1915. On the 29th of May 1919, Arthur Eddington, on a famous expedition in the South Africa, he found out that yes, during that solar eclipse, light really bends, and that happens due to the space-time curvature. So the gravitational time dilation and the deflection of light by gravity was confirmed by Eddington's 1919 solar eclipse. Now, if you look in understanding general theory of relativity as a whole, you will always get into internet or blogs or any books, this type of things. Now, what these explain is that this is correct, this one is correct, and this one is equally correct. Although some authors and physicists say that this is not a perfect or a precise way to describe general relativity. Now, my idea is that all these diagrams, what they tell to you, they give you a fairly intuitive idea of what general relativity is all about. And it says three essential things. There is a heavy object on a fabric, it creates a dent, and that dent is on a grid. So the pictorial understanding of what we see right now on the screen gives you a fairly intuitive idea of understanding general relativity as a kind of a geometric understanding of physics. If you go to Google and type out this word, what is general relativity, you will come across these very famous and known websites. And all these websites actually reflects one common word, that is, it is a theory developed by Einstein. It is a theory of gravity. It is a theory which talks about space-time, geometry, etc. and etc. So from here we can understand that it is basically a study on the curvature of space-time, and this curvature is caused by the presence of mass and energy, and that heavy ball actually is a source of creating the curvature. Now the question on this part of our video is that what actually causes the curvature? And for that we have to really understand these two concepts, space-time as separate identities and space-time as a whole. Coming up in the next part of our video, how our understanding of space-time shaped in our current understanding of general relativity. Now, prior to Albert Einstein, time and space were considered by Newton, Galileo, etc. as two separate identities. Now, the uniting of space and time into a single entity, which is called a space-time, actually made a fundamental geometric change. So as we start with special relativity, it reinterprets them as coordinates in 4 dimensions. And what we get is this. And this is called a space-time continuum. And this is something which is treating space and time not as independent entities, but as a single identity, and it is on a 4-dimensional geometric structure. Now, this key information is here, that the distances and intervals in time are no longer absolute but mixed. So when we talk of space-time measurement, we generally start with what is called the famous Pythagoras' theorem. Now, this Pythagoras' theorem gets further extended into this. Don't worry, this looks intimidating, but I will just explain you. This is what is called a space-time intervals, or you can say right for the time being that this formula actually calculates the distance, angles between points, etc. It is a kind of a metric, it is a kind of a measurement, but not in a separate space-time metric, but in where space and time is together. That is a 4-dimensional metric. Now, this can further be extended in this kind of a tensor notation, which is called the metric tensor, which is applied from flat spacetime to curved spacetime. Don't worry about these terms, we will explore, and I'm going to explain you very easily. So as we rotate a particular particular coordinate, but still the distance between those coordinates or the points remain the same. Same thing happens in special relativity, that Lorentz transformation mix space and time while preserving the interval. So this concept is generalized to a dynamical metric that depends on what is called space-time coordinates. Well, all in all, what I am trying to tell is that, see, if space and time are now united, then what happens if the space changes? Well, what do we mean by space change? We will come in the next part of our video. But before that, I would like to give you a pictorial understanding that imagine this to be a kind of a lump where space and time are together united. So this is a space-time continuum. And each of these blue dots that you see inside the circle. Over here, this is space-time. Over here, it is also space-time. Over here, it is also space-time. And over here, it is also space-time. So that means these blue dots are not denoting space or time as separate coordinates, but as a space-time as a whole. So what I'm trying to tell is this, that space and time are not separate. So if we make a change in a space, then obviously time is going to affect. If you're going to make a change in time, space is going to affect. Why? Because they are all interconnected. And this led to a profound change in our understanding of space-time, and that we will explain in the next part of our video. Now, I want you to imagine this as a light clock. Well, light clock is something which you cannot just go to a store and find it, but it is a kind of a equipment, and it tells that this is a light clock. So here is a tick when the light hits at the bottom of the mirror, and this is a tock when it goes right up it. So we can say that a light clock is basically designed so that a distant mirror, there's a flash of light which is going and coming. Tick tock, tick tock, tick tock. So two parallel mirrors are being installed and a beam of light bouncing back and forth between them. For the time being, you can just imagine this red dot. And the time it takes for the light to go up and down, I would say it is a proper time, is denoted either by delta t or by delta t 0. Now, this can be extended to a Rolex wristwatch, to your grandfather clock, or whatever you want to take. But the basic essence is why I'm taking a light clock is that I want to avoid all those intricate and complicated mechanism of a clock and take this one as a ideal clock. So one tick at the bottom and one tock at the bottom, you can tell it as a cycle, whether it is second or minute doesn't matter. Now we are extending this light, this tick tock over here. So let it go up and down, tick tock, and I am imagining this to be the light clock. Now this light clock, now I am trying to move. So I'm holding the light clock and I'm starting to move. So the tick takes place over here, the tock takes place over there. A person who is holding this clock right at this moment can see time going up and down, up and down. Now when I'm moving, say for example, the first tick happens over here and the next tock happens over there. So you can see that the line is a little bit, I would say, it is not a straight line. It's not a straight line, it is a little bit slanted line. And again, from the tock, the next tick takes place over here. So the line goes diagonally over here. And the next tock takes place over here. And the next tick takes place over here. So the lines, as you can see, are quite extended, are not straight lines. So what I can tell you is that this person who is watching the clock from outside, what he sees that moving clocks run slow from an outsider's perspective. However, this person who is standing over there, who sees that delta t, for him the time is absolutely perfect. There is no change. And the clock is just going tick tock, it is sitting at the bottom, at the top. But for the person who is standing outside, as I have seen those, you can see those black lines, those arrows actually indicate that the time has been more. That means the time is taken a little bit longer because the lines are a little bit more diagonal. Now let us take this example forward, and if I move a little bit more faster, so the tick takes place over here, but I am moving a little bit faster, for example close to the speed of light. So the tock takes place here, and now you can see the diagonal line is further extended. And again the tick takes place over here, the diagonal line is further extended. So from here what we can say, that path is longer compared to that of the stationary clock, which is going tick tock, tick tock, tick tock. So the person who is standing outside, longer path but the same speed of light, this denote that the tick tock happens at a slower rate. And whereas this person, the slow tick tock means time is on moving clocks run slow, and the light path is diagonal up and diagonal down. This is a wonderful thought experiment which gives you an idea that why on a moving frame or frames which are moving close to the speed of light, why clocks run slow. Now here is an important note. It won't happen that from here, say from Bengaluru, you can move to Netherlands in say 20 minutes time or 10 seconds time. Even that speed is slow. So you really need to get this difference physically, you need to move at the speed of light. Now, this thought experiment actually solves a lot in our understanding what is called a twin paradox. So we go ahead with the same clock, the light clock, which is going tick-tock, and here is Alice standing on the surface of the earth, and on the same time his twin Bob starts off on a spaceship, and he goes from a tick to talk over here, and then from again this talk Bob goes on a flying spaceship, and it takes place over here, tick. So you see the diagonal lines are longer, and you can imagine if I'm moving to the space of the speed of the light, how long the diagonal would be. It would be quite long. And from here, when Bob returns back to Earth, he sees that Alice has grown older. And the reason is that your entire biological clock, your genes, your heartbeat, which follows a natural path, this has been slow. Why? Because of this reason. If you move close to the speed of light, time runs slow for you. So when Bob returns to Earth, he finds that his friend, or you can say his cousin Alice, has aged much more than him, because time on Earth is just going tick-tock, normal time, but on space it is going much slower because he is moving close to the speed of light. So his entire gene, his structure is going less. Now, this is a kind of a pictorial understanding of how clocks run slow in a moving frame close to the speed of light. So from here we can understand that time dilation and special relativity happens due to motion. And we measure this using the simple time dilation formula. And from here what we say is delta t hash, that is the person who is moving in the moving frame, and delta t is the measured in the observer frames. And in this case we say this gamma is a Lorentz factor. In a very simple language, you can say it is a number that tells how much time, length and mass change when an object moves close to the speed of light. Now, there can be numerous mathematical calculation in terms of Lorentz factor, and I also have made a video on the mathematics of special relativity, few exam question and answers, but that is different. Whatever is important is that if this you are moving close at around 10% of the speed of light, the almost of it has got no effect. That means the gamma factor is very less. If you're moving 90% of the speed of light, then the gamma factor is more, 2.3, and it has got a big effect. And if you're moving close to 99.999999% of the speed of light, gamma factor is more. That means the effect is huge. So we have seen how the light clock actually shows that moving clocks actually run slow, and this is the mathematical calculation using Lorentz factor, and how moving close to the speed of light the Lorentz factor increases. Now this is okay with special relativity because we are moving in a flat space, but what about this? I would say when this particular things come up, it is a black hole. And for example, the same tick-tock clock is ticking, and this astronaut is falling inside the black hole or coming near to the black hole. Not only black hole, a very high gravitating object. So time for this astronaut would be ticking perfectly, just as we have seen tick-tock, tick-tock. But for an astronaut or a person low, the time is slower. So a tick over here will give you a talk over there. So for this person, time slows down. Now here is a little bit of difference. Understand that in special relativity, this time dilation is because of speed, but in general relativity, it is all because of curvature. Now what do I mean by curvature? Let us say, for example, this is the rubber sheet and an ant is crawling, and then there is a dent. The rubber sheet collapses due to paper weight or any mass and energy, and you see the ant's path is going down and down, just as the way I have showed you that there's a tick and the blue arrow goes down and there's a talk much later. But remember, in general relativity, it is all because of the gravitational potential. It is because of gravitational potential energy and due to curvature that this time dilation and many other things happen. And one of them is what is called a red shift, where you see that the energy is getting shifted and there's a red shift. And just opposite to that, we have got a blue shift when the frequency is much higher. So redshift, blue shift, we have watched this in astronomy, in galaxies, etc. When due to energy loss, the wavelength is getting stretched, etc. So all of this actually happens due to the space-time curvature, due to the high curvature, and the measurement takes place in this curvature and gives this result. So from here, what we can say is that time dilation general relativity happens due to gravity. And say, for example, you place a clock which is closer to Earth, that means it has got a high gravitational potential. This will run slower compared to that which is far above. So we use a similar kind of a mathematics to calculate that, and this one is basically called the time experienced by someone closer, something analogous to moving frame. And delta t, you can understand, is time experienced by a far away observer. That means in special relativity observer's frame of reference. This m is the mass of the object, g is the good old gravitational constant of Newton, and r is the radial distance from the center of the mass. So here you can see that if you put an object which is creating a high gravitational force, so near a massive body space stretches, and since time is linked, so time will slow down, and the clock takes slow near a gravitational field. Now till now everything is going nice and fine, but what we need to now understand is that when space and time is united into a space-time continuum, there are certain limitations which happens in terms of Newtonian mechanics, the mathematics, and for that we need to design or define a new way of dealing with those, and these are called four vectors. And this actually measured a kind of a movement or a metric in space-time, but this also have got a limitation. First, let us see what are four vectors. Now in general, four vector we can say it is, so here it is, because time and space is now united in space-time, and because we need a new mathematical tool so that it unites space and time together, we call this new mathematical tool as a four vector. By definition, we can say a four vector is a mathematical object that combines space and time in a single identity. So this is the ordinary vectors which only describe space but not time. I mean to say they can describe time but distinctly, not taken together. And ordinary vectors, remember that they rotate under Galilean transformation. Here we need a Lorentzian transformation, and position, momentum and velocity in classical mechanics, they are not invariant. So here is a definition of four vector. It is a four-dimensional vector in Minkowski spacetime. With Minkowski spacetime means flat spacetime that transforms under Lorentz transformation. It looks something like this. This x mu is the time component, and generally we will see that it is c times t, where c is the speed of light, and these are spatial components to normal 3D coordinates. So, and there can be other vectors, and this is invariant under Lorentz transformation, so that is a good news for us. And there can be others like position vector, 4 vector, velocity 4 vector, and force 4 vector. So all the vectors which we see in Newtonian mechanics now are united in a single identity, which are called four vectors. Now the first kind of four vector is called a space-time four vector. Here you can see. So in special relativity, first of all let us see this part, this CT part. In special relativity, space and time are connected through the speed of light, because the speed of light is, as we know, is a universal constant, and same for all inertial observers. So the speed of light, we can say, acts as kind of a conversion factor between space and time. X, Y and Z are the spatial coordinates. And remember, this is also a rank 1 tensor. So that means tensors can generalize four vectors, as we will see later. And the next type of vector is what is called the energy momentum four vector. Here also you can see this is the total energy, and these are basically the coordinates multiplied by the speed of light. So these are three spatial dimensions. So why we are multiplying the three momentum by the speed of light? So that we get something which is called a relativistic momentum. And remember that these four vectors actually they obey what is called a Minkowski metric, which is denoted by the Greek letter eta. And this something looks like this. What are the meaning, etc., we will come later. And this eta mu nu later gets generalized into a tensor component, which is called the metric tensor. So right at this moment for our understanding, we understand that the good old Newtonian mechanics, the vectors are insufficient to define a relativistic momentum or a relativistic force vector, etc. So we need a mathematical tool to unite these three into one, which is called a four vector. But as we will see that there are certain limitations of four vectors which led again to a new formulation of mathematics. In this part we will quickly look across what are the limitations of four vectors. Now the first limitation that we get is that four vectors are definitely very good in understanding events in relativity, but they cannot describe what is called an electromagnetic field. Now, four vector cannot encode the relationship between the electric and the magnetic fields in different frames. Second is that they cannot describe stress, pressure and energy flow, because what it does is that a four vector can describe energy momentum of a single particle. But when we get a continuous field kind of a concept, describing energy flow, stress and pressure become difficult. So the stress energy tensor is a rank 2 tensor that generalizes four momentum, density and flux. We further see that the space-time curvature, which is actually denoted by a very complex mathematical tool which is called a Riemann curvature tensor, four vectors cannot do that because it cannot take care of all those indices, covariant and contravariant. As we have mentioned that it only transforms but not it is Lorentz invariant. Also, the Lorentz transformation, as you can see, they cannot be expressed. All in all, what we can say is that four vectors are good in special relativity, but they cannot describe relativistic physics, where space-time curvature, angular momentum, and some aspects of quantum field theory also comes in play. So from four vector, we now generalize and design a new mathematical tool which are called tensors. Let us first look in from four vectors, how do we move to tensors, and then we will understand that how the role of tensors are important. So here I would lay you out the key differences between four vectors and tensors. So four vectors has one index, it can have multiple, that means dimensions etc. are much more sophisticatedly handled in tensors. It is used in flat space-time, it is in curved, and this transforms under Lorentz transformation. This is under any general coordinate transformation, and it represents individual physical quantities. This represents physical laws across space-time. So the four vector that we have seen, the momentum four vector here, as you can see, this gets generalized into what is called stress energy momentum tensor. And then again it gets a very important place in Einstein field equation, where this T mu nu comes as a source of curvature in Einstein's field equation. And the stress energy momentum tensor in terms of matrix something looks like this. And here you can see this T00 is basically the energy density, total energy per unit volume. And then these diagonal ones, which you can now see, T11 and so on, these describe normal stress pressure in XYZ direction. And these one, the non-diagonal or the off-diagonal components, they describe shear stress of different layers of medium, and they pass each other. So what we can say is that the stress energy momentum tensor, the four vector was a rank 1, this is a rank 2 tensor, and it describes energy, momentum, pressure and everything, and it acts as a source in Einstein's field equation, which is responsible for the curvature. Also, we can see that in classical mechanics, for example, this particular is called a position vector. Now, in position vector also gets generalized into what is called a metric tensor. Now, try to take a moment to understand what do we mean by position vector. Position vector means where we are trying to assign a particular position, a point, a line, a distance from one point to another. The metric tensor does the same thing. That determines distances, but it gets much more generalized because there are a lot of complex mathematics to follow. The classical force F equals to ma, where m is the mass and a is the acceleration, you can say dv by dt. This classical force is generalized into what is called a 4 force. And this one is because 4 force apply to individual particles, and this is I would say this classical 4 force where this momentum can be defined as this. This can be taken care into 4 force takes the form of this, and then it further evolves into stress energy momentum tensor, which is actually which describes energy and momentum in Einstein's field equation. So as you can see that the evolution is quite smooth. From classical force we go into 4 force, then there are problems, we get into tensors, and then we get into Einstein field equation, which actually describes the curvature. Then if we turn our page, we can see that the classical velocity also gets generalized. Here you can see I refers to components of x, y and z. So the problem is that time and space are treated separately, which does not work well with special relativity, where time is also a coordinate. So it gets into what is called a 4 velocity. Now here you can see that tau, we switch to proper time tau, which is a time measured in the object's own frame. And this can be generalized into, which are the components into this. So we get a Lorentz factor, then we get Vi, which is the 3 velocity, x, y and z direction. And this one shows that time slows down, the time dilation, and it shows the relativistic velocity. But velocity again had caused a little bit of complexity, because in curved space-time, this would be dealing with what is called a geodesic equation. Don't worry, this equation we are going to take a look. But before that, this is the evolution from Newtonian mechanics to 4 vectors, limitations, and finally into tensors. Now, before we move into tensors, these tensors and these 4 vectors actually calculate what are called distances, lines, and these are in relativistic terms, these are called events. And this leads us to the next part of our video, which are called light cones and space-time interval. But first, we need to understand what is a space-time interval. Let us look in the next part of our video. So intervals means what? That in a film there is an interval. Interval means gap. Here also we are trying to find a gap or a distance between that. And this is done by what is called the ds square. You have seen this ds square in the space-time interval in Pythagoras' theorem. So what we can say is that in simple terms, the space-time interval is a way which measures the distance between the 2 events. Here you can see from Pythagoras' theorem, which is 2 dimension, we are shifting to 3 dimension. So ds squared now become equals to dx squared for the x coordinate plus dy squared for the y coordinate and dz squared for the z coordinate. So here is a quick nice definition. It just measures simple things, the distance between 2 events in space and time, just the way we measure distances between 2 points. Now, one thing we have to remember that when we are measuring distances in space-time, moving forward in space and forward in time don't add up in the usual way. Instead, we would say more movement in space makes the total time interval smaller. We called it space-like, and more movement in time makes the total interval larger, which is called a time-like. And this equation is actually the what is called the space-time interval. So this is the Pythagorean, and this is in a 4-dimensional space-time. So this Minkowski metric leads to something like a light cone. We will explore this wonderful object. So there's the tip of the cone, the present moment, the inside of the cone, all events you can influence, the past light cone, all events that could have influenced you, and outside the cone, it is inaccessible by light. So this ds square has got 3 things. One is which is called time-like, the second one is called space-like, and third one is called light-like. We will look in that. But among this entire equation, do you find that there is a negative c squared? Now this has got a profound influence, although there are derivations which I'm not going, but minus c squared dt squared actually means that it ensures that the speed of light is the same for all observers. It also guarantees that the speed of light is the same in all frames, and without the minus sign there would be no maximum speed, and the entire edifice of special relativity will collapse. So this is what is called a space-time interval. It is just the distance between 2 points. From Pythagoras, we move to 4 dimension, and when we move into 4 dimension, we get a nice structure which is called a light cone. Now let us look in the light cone and let us understand what it actually means. So first of all, this point, the yellow one, the surface of the light cone actually what is called null geodesics. That means here are the paths that light rays or photons follow. Since the photons travel at the speed of light, their world lines always remain on the surface of the light cone. So that is why I have put the point on the surface. Next comes this red one. This is where it is called time-like geodesics. That means these describe the motion of massive particles which move slow to the speed of light. Because massive objects geodesic must always stay inside the light cone, meaning it cannot exceed the speed of light. Third comes the blue one, which is called the space-like geodesics, ds square greater than 0. This implies faster than light travel, which is not possible, and these geodesics do not correspond to the physical motion but are used in some mathematical treatments. So we can further put this one as light-like, this one as time-like, and so on. So time-like geodesics, light-like geodesics, and space-like geodesics. These three things are very important. And when this comes up on a flat space, so you see all the lines in the light cones, they are flat. There is no amount of curvature, and this is the typicality of special relativity. So in special relativity, the concept of geodesics is introduced, but it is not a typical geodesic. It is just a simple straight line. So it is calculating the interval, which are these three types of interval. Now, as we have learned about the Minkowski metric, which is this eta, and this can be written in a matrix forms minus plus plus, and this can be further told as a 4x4 symmetric matrix. In a symbolic form, it is written as eta 00, eta 01. But don't worry, this eta 00, eta 01 all have values. And you can see it is minus 1, then some are 0, then some are 1. So it can be put up in here. So that is how it looks like. So those which are equal to 1, these terms apply to what are called spatial components. Here it is. These are 1. So as you can see, eta 11 is what? 1. Eta 22 is what? 1. Eta 33 is what? 1. So these are all 1. So 1 actually means that they indicate spatial distances just as measured positively, similar to the school level geometry, Euclidean geometry. And they indicate that the spatial distances are measured positively. But those which are 0, for example, you see there are a lot of zeros. These are the time does not influence spatial coordinates directly. We can say that the different spatial coordinates do not mix each other in Minkowski spacetime. Now here is a note, I would say a conventional difference. In some of the books you might find this to be this. And this shows the matrix to be minus plus plus, and the interval looks like this. But also in some of the books or some of the learning methods, you will see the minus sign comes over here. 1 minus minus 1. And this is the metric which is as plus minus minus minus. So this the space-time would interval would look like this. So both of them are correct. So here is the -1 and here is the -1. So both conventions are correct. Both of them work. But it is important that when you are using and on which type of a metric. So from here till now, what we can understand that light cones are basically space-time intervals, three types of space-time intervals, but all on flat space. The question that comes to our mind is that how the equation will look in a curved space-time. These are all flat space-time, but how the equation will look in curved space-time. And for that we come to the next part of our video, which is called space-time curvature and geodesic equation. Well, when we move into general theory of relativity, obviously we are taking a sphere, which is more or less easy for us to understand. And this is what is the geodesic equation looks like. The alpha, beta are sometimes replaced by many other indices, but don't worry. We will go in this part of the equation one by one. First of all, let us understand what this equation is. It actually governs how particles moved in curved space-time. In the absence of external force. We will come to this part in the absence, very important. First of all, let us see this x mu. These are space-time coordinates and the index runs from mu to 3. That means, okay, we will come to that a little bit later. I will expand on this. First, the overall, the tau, this is called the proper time. Then we get this particular gamma with a mu, alpha, beta. These are Christoffel symbols. We will look at that later. And there is another term which is called 4 velocity components. Doesn't it sound resemble similar to the 4 vector? Yes, it is more or less same, but a little bit of refinement will help things learn better. So x mu is basically running from 0 to 3. 0, 1, 2, 3 and the x, y, z components. This represents coordinates in space-time. Okay, d square x mu and d tau square is nothing by acceleration. Remember acceleration's formula in Newtonian mechanics, second derivative of position divided by by time. It happens same over there. It is nothing but the acceleration. So if we set the acceleration 0, I mean to say in that case there won't be any kind of a curvature. So we are done with space-time coordinate. We know what is a proper time, and now we understand this is basically nothing but the component of acceleration. Now, if we look in the next part, which is called the Christoffel symbol, these are nothing but connection coefficients. Connection coefficients that tells that how the coordinate system changed in curved space-time. Let me go back here. Now here you can see that if it would have been set to 0, things would have been different. But we put what is called a plus. That means we are adding with acceleration another term which is called Christoffel symbol. So the Christoffel symbols describes a movement in one direction. Say for example alpha influences movement in another direction beta. Again Christoffel symbol ideally could be set to 0 for flat space. So the motion of a test particle is affected by space-time coordinate and the direction in which it moves. So these are the space-time coordinates, and this alpha beta determine how different coordinate directions affect motion. That means motion is now guided by two things. We will come what are the two things. But first let us understand that the motion of a test particle is affected by both space-time coordinate and the direction in which it moves. This is a stark difference between Newtonian mechanics. So here in Newtonian mechanics it doesn't happen because motion can be curved. Here the motion is curved. Acceleration at point depends on both where the object is moving and in which way it is moving. I will just explain it in a pictorial understanding. So now we understood the Christoffel symbol acceleration. Now we come to this one. This is the first for velocity and this is the second for velocity. What does it tell? The first velocity tells how fast we move in the direction of alpha. The second velocity tells how we move in the direction of beta. And the Christoffel symbols also, remember, they carry both the alpha and beta terms. That means they tell how these two velocities interact in space-time curvature. So that alpha beta, which is there in the first and the second velocity, have to be there in Christoffel symbols because this is a correction factor. Now I will try to address this question that why there are two velocities. The reason is that the two velocities terms appear here because the curvature does not just depend on where you are but also on how fast and in which direction you are moving. That means the Christoffel symbol actually modifies acceleration based on both the coordinates, and that is why you see alpha and beta. So if the road is just straight, you move straight. If it is curved, your motion in one direction influences another. Think of this roller coaster. For example, here if you're moving, there's an acceleration. It depends where you are on the track and how fast you're moving in different directions, the velocity components. So from this part of the video, what we can understand is that space-time, if you're moving only in one time direction, curvature affects you differently than if you're moving both space and time. And that is why the effect of space-time curvature is quadratic in velocity. So you see from the space-time component how we united space-time into one, and from there we went into 4 vector. That carried a problem. We went into tensors, and because space and time is united into one, all this, I would say, complications actually starts taking. And that is why there are two velocities, two factors which are involved. So if I take the Newtonian acceleration, which is change in velocity by change in time, here remember that the acceleration A depends only on position. If you take the gravitational potential, and there is no dependence on direction of motion. That is very important. So that means that in the Newtonian gravity does not depend on the velocity of the particle. So here but not by velocity. Gravity acts the same way. So if I take a gravitational force, for example, if I take this part and if I put a mass over here, I put a little nice mass over here, and what you can see is that if you place a particle at a certain point, then its acceleration is fully determined only by the gravitational field at that location. But in case of Newtonian mechanics, gravitational force is same whether the particle is moving up, whether it is moving down, whether it is moving left, or whether it is moving right. Only position matters. So Newtonian physics, motion is affected by position but not by velocity. Gravity acts the same way on all the objects regardless how fast they are moving. And here is a nice diagram. Say for example, this is a curved path. Why different velocities experience different effects. And this car is moving. So it will depend both on the position as well as in the direction. So from here what we can get, there are two important things. If motion of an object is moving radially, that means towards or away from a massive object, time dilation, gravitational acceleration are strongest. If an object is moving tangentially, for example, orbit, any sphere, any orbit of planet, spatial curvature affects it differently, leading to certain precision effects, which we have seen the Mercury's orbit. So from here, what we can say finally, after looking in all those mathematics, is that velocity is how an object moves through space-time. And here, curvature describes how space-time itself is shaped. This curvature takes place or features in Einstein's field equations. And remember, space-time curvature is what causes velocity dependent, but velocity obviously is not the curvature. The geodesic equation that we saw over here, this Christoffel symbol acts as a correction factor. That means it actually corrects these two parts, the 4 acceleration, this part, and when we take these 4 accelerations, it actually tells that they multiply each other because space-time curvature couples different velocity components. Now, this is an important thing. When I say the word coupling, I don't say it is multiplying. Coupling means two things are connected and one affect each other. So in electromagnetic fields, when we say an electric field and a magnetic field are coupled, we are not saying multiplying, but we are saying because a changing electric field creates a magnetic field and vice versa. So here also, when we tell that different velocity components are coupled, we are trying to mention that because curvature makes motion in one direction, effect on the other. So here is a nice, I would say, summary of the space-time curvature and geodesic. Space-time in Minkowski has no gravity, so no acceleration, object moves fairly in a straight line, and geodesic equation is just simply 0. In general relativity, mass energy tells how to curve objects for geodesics, and Christoffel symbols are 0 in case you are taking curvature as 0, which is not. Here you can see these are the two components of 4 velocity. Motion is governed by geodesic equation, and since space-time itself is curved, Christoffel symbol adjusts and take the alpha and beta direction of motion. And since motion in one direction influence motion in another, velocity components appears twice. So this covers and clears our concept of space-time curvature, how it happens, and what equation, geodesic equation, guides it. Now there is an obvious question which you might ask, is that why the geodesic equation is set to 0. We understand in flat space-time there is no curvature, so that can be set to 0. Here we have still got a curvature, isn't it? But still, why we are saying that it is 0? The answer is pretty simple. The answer is that it means that there is no acceleration, I mean to say any external force, and there is no additional force acting on the particle. So when it is set to 0, this acceleration is set to 0. It implies that free particles move in constant 4 velocity. That means there is no acceleration, it is constant. But when we say the geodesic equation, it involves acceleration. So we are not setting acceleration to be 0. We are setting the equation to be 0 to mean that there is no external force. Now, what do we mean by external force? That I would like to show you. Now, imagine this is Earth and this is a small, nice little test particle which is moving in this trajectory. Okay, and I will try to move this particle, and here it moves. Now, understand that when this particle is moving, the person who is observing from outside, what he sees that the particle moving on a geodesic, for this person, it obviously is accelerating. That is why it is moving. This is acceleration. But actually, in terms of general relativity, it arises naturally from the curvature of space-time. There is no force. So this acceleration is not caused by a force. It is basically just following the natural path, which is the geodesic. And that is why it appears to the external person that it is accelerating. However, it is just following the straight path. So there is no pushing or pulling of force which is causing the particle to accelerate. It is instead the particle is following the straightest possible path. And here is the ultimate final we can say line, that acceleration is a consequence of the geometry of space-time itself. There is no acceleration as such. It is just a manifestation or a consequence. So curved space-time actually dictates and tells the path of the particle where to move. And for the outside observer, it seems that they are accelerating. And this led to a very famous understanding of equivalence principle. Now say this astronaut is slowly falling. So an object, astronaut, when this person is falling, say, let me show you the animation once more. Yeah. So an object in free fall feels no force and moves along a geodesic, which we have just seen. This means the astronauts in orbit experience weightlessness even though they are accelerating in the traditional sense. So but in Earth coordinates, it would be accelerating as 9.8 meter per second square. That is basically what is called the coordinate effect. So the geodesic equation, why now it is set to 0? Because according to the equivalence principle, free falling objects have no force, although seem to be a force. And that is why the geodesic equation is set to 0. So the equivalence principle tells that free falling objects experience no force. They're just moving along the trajectory, naturally path. And that is why, because there are no force, we set it to 0. So we come to the last part of our video where we just do a quick summary of what we have learned. First, we have looked into the birth of general theory of relativity, Einstein-Grossman paper, which finally was discarded in 1915. Einstein published his general relativity. Uniting of space and time, which led to a lot of consequences, the four-dimensional space-time, and it is united into this kind of a four-vector. Then we learned how moving clocks run slower, and we learned it nicely with the usage of this what is called the light clock going up and down tick-tock. And also in case of a highly gravitating object, times run slow. We have seen how four vectors get generalized to tensors because they have certain limitations, and in tensors they generalize into a complete way where they are also transforming under generalized coordinates. We also seen Minkowski space, which leads to two type of intervals, time-like, light-like, and space-like. This metric gets further generalized into geodesic equation, which is the Christoffel symbols comes as a correction factor. Velocity and motion in curved space, we have seen that velocity depends only on position, hence things move in a straight path, but here it is influenced both its position and its velocity. And the biggest, I would say, difference is this one, that the Christoffel symbols acting depending on the position in space-time. These are calculated from the metric tensor, this one, G mu nu. And the metric tensor turn, I would say, in turn depends on the distribution of mass energy curvature. So what we learned specifically is that the four velocity, the position dependence is very important. It involves the components of the particle's four velocity. It means that the motion of the particle is also influenced by its velocity. And the Christoffel symbol encodes the curvature of space-time. So the position dependence, which is in Newtonian gravity, that gravitational force depends on the position of the particles relative to the source of the gravitational field. In general relativity, however, as we discussed, the acceleration due to gravity in Newtonian physics is independent of the particle. But in case of a general relativity, velocity also plays a key role in determining the motion of particles, whereas Newtonian gravity, it does not. So this is, we can say, in general relativity, the motion of a particle is influenced by both its position and its velocity, and this is a fundamental departure from Newtonian gravity, where velocity has an impact on gravitational acceleration. Finally, we also learned what is a space-time interval and what that minus c square implies, and in general relativity it generalizes to metric tensor, and why the geodesic equation is set to 0, not because acceleration is 0, but there is no additional force. And in case geodesic equation has got some value, for example this one, it means there is an additional force per unit mass. So that brings us to the end of a fairly long video with a lot of mathematics and understanding. I would like to take a moment to thank you very much for taking time and watching this video. If you have liked, please do subscribe and click on the subscribe button and click on the bell icon to get all the notification from Physics for Students. And on my channel, General Relativity Explained, there are quite a number of podcasts and very good detailed videos of General Theory of Relativity, which I am trying to put together. So also do subscribe to this channel. Thank you very much, and I will be back soon with more interesting and fun-loving videos. But till then, may the good Lord be with you.